So yeah, my talk is on modeling peeling of soft adhesives, also known as pressure-sensitive adhesives, or PSAs. And they are useful for a wide range of different everyday applications, from like that bottle of water. And in my particular case, I work on drug patches. So kind of like a nicotine patch, but in this particular case, it's for infected nails, which have fungal infections like that. That was the nicest looking image I could find. Sorry. And so when you have that an infection like that, you want to actually apply the drug directly to it. So we want to develop a patch that you can just stick onto it. So the patch itself will consist of a backing membrane, the PSA with drug in it, and then in this particular case, for my testing in the lab, I use a polyethylene substrate because it has a surface energy which is quite similar to the nail. When you're making a drug patch as well, you want to be able to stick it on. It has to actually stay there for the desired amount of time, and then remove it cleanly. So unlike that picture at the bottom where you see the adhesive is like debonded from the backing and stuck onto the substrate, that's not what we want. So the overall aim is to simulate the peeling process, and in any type of simulation or modeling, the model is only as good as the input parameters that I put in. So in this case, I need material properties for the backing membrane, the adhesive itself, and the interface where it will debond. So here's just a simple schematic of what the peel test looks like. You have the backing, the PSA, you have the substrate, and then you have it on a rolling rig so that you can maintain the constant angle when peeling. You can just see a zoomed in region of it, and you can see the backing membrane, the PSA layer, and those are the properties I want to obtain in order to run my simulations. So I've deconstructed the patch, like I said, into the backing, the pressure-sensitive adhesive, the interface, and the substrate. In the case of the substrate, which is the nail or the polyethylene, I'll be modeling it simply as a rigid body. So I'll start with the backing membrane. It's a PET film, Scotch-Pack 9757. I've tested the tensile test at different rates, and there's more or less rate independent. And I can model it very simply using power law material, so I just have a modulus, and then, the power law fits the plastic part of the stretch strain curve. In terms of the adhesive, I then have the bulk adhesive, and I've done tensile tests on it, as well as relaxation tests, and this time around, it's not as easy as the PET film, where you can see I clearly have rate dependency, and also it's not linear as well. So I need to model it differently, and I've decided to use a viscohyperelastic material model, which takes into account both the strain dependence and the time dependence. So for the time-dependent part, I use a Prony series and determine the different time constants, and you can see it's divided into the long-term elastic part and the viscoelastic part. Now in terms of the strain-dependent part, I use the Van der Waals hyperelastic material model, and then combining them into one, essentially all I just need is the time and strain history for any kind of loading, and I can determine what the stress is. And applying this back to my original data, you can see that it fits quite well, which means now I can model my PSA. Which now brings me to the interface, where I said I was going to use a cohesive zone model. The cohesive zone model, looking at the traction separation law, the simplest case is a linear triangular fit, and it's divided into three parts, where I have the initial stiffness K, the maximum stress, sigma max, and the fracture energy, which is the area under the graph. In my models, I've made K as stiff as I possibly could to reduce the compliance in the system. And in order to get sigma max and the fracture energy, well, fracture energy in particular, I could get that if I did a peel test and then use an analytical fractal mechanics model to get fracture energy. But it's a bit of a loop because I do a peel test to get fracture energy out and then I stick it into my peel model. So I figured I'd try a totally independent test. So I decided to do modified probe Tack tests. So you can see the probe, the PSA, and the polyethylene up there. Initially, the probe comes into contact with the PSA. It compresses it for until a certain force, known as a dwell force. Leave it there for a certain period of time, called the dwell time, and it relaxes. And then I pull it off, in tension, at different speeds until there's failure at the PSA polyethylene interface. Converting that graph into stress versus displacement, kind of like my traction separation law, you can see that there's a rate dependence. And the two parameters that I want are the area under the graph and the maximum peak stress. Now you can see, like I said, I did the pull-off part at different rates, and there's a rate dependence for the Tack strength, which is the maximum strength, as well as the Tack work of adhesion, which is the area under the graph. And so I've called that WA, and in this work I've assumed that the Tack work of adhesion is equal to the fracture energy. So I've done 3 different sets of tests, and now essentially have everything I need to put into my model. I have the backing material parameters, have the adhesive parameters, and I have the interface parameters. So this is the finite element model. This is, you can see the mesh, the adhesive, backing membrane, and then contour plots of the strain, which is mostly in the adhesive. Stress, there's the backing membrane is plastic. And then in terms of the energy dissipation, all the work that goes into the system, it goes into either tensile deformation of the entire peel arm and bending of the peel arm. There's some plastic energy dissipation as well. And in this particular case, because it's a PSA, there's also a viscoelastic energy contribution as well. And then, of course, the fracture energy at the interface. And here you can actually see the force displacement graph at different points during the peel test. So you can see initially it bends until I get a steady state force. So it seems as though my peeling model works, but naturally I need to go into the lab to actually validate it and make sure that my model is correct. So purple dots are what the FE model predicts. Green bars are experimental. I'd say it's a pretty good match. And relating this back to a drug patch, as the angle increases, you require less force to remove it. So that's a good thing. In terms of the speed at which I'm peeling this off, as you increase the speed, you have a higher force, which, again, relating it to a drug patch means it's more painful to remove if you're removing it really quickly. So in terms of pain, you either pull it off really fast and it's a higher force, so it hurts more for a shorter period of time, or you pull it off slowly, hurts less but for a longer period of time, so I don't know, somewhere in between. And then the last part is the thickness of the adhesive layer. As the thickness of the adhesive layer increases, the force required to pull it off increases as well. Now the importance of this is the more adhesive layer that you have, that means you have more drug in your drug patch, which in theory means you can keep it on for a longer period of time before you have to replace it. And on the topic of drugs, I'll just conclude my talk by saying, now that I know this entire methodology works for the pressure-sensitive adhesive without drugs, we're now going to apply it to adhesives with drugs. So essentially just use the viscoelastic material model for the PSA, and then use the Tack test to get cohesive zone parameters, and then essentially stick it into the FE simulations and vary the parameters of speed, thickness, and peel angle until we can find the perfect combination for all 3. And that's the end of my talk. Thank you very much.